Hello, good morning. Thank you all for being here and being interested in this talk. I'm going to do it in English because I cannot possibly do it in Polish yet. Um, my name is Jeronimo Martinez. I'm a software engineer at DataArt, and today I'm going to talk about the Eta lang. So you may wonder, what is Eta? Have you ever heard about Eta before coming to this talk? You raise your hands, you know, yeah. Okay, that's two people. At least you know it's a programming language, right? When I told my family and friends in Spain that I was going to talk about Eta, they asked me if I have become an expert in terrorism. Um, from that point on, I always say Eta programming language, just to make it clear that it's not the other thing. So why Eta? So for a while, I've been learning and playing with functional programming for a few years. And it's not just a different way of writing code. I think it's a better one. In this talk, I'm trying to show you why I think so. So Italan was a nice thing to have. I found that 1 year ago or so, and it's really nice and purely functional. So it's a really good match for if I want to talk about functional programming in a Java conference like this. So let's jump in. First, I work in DataArt, so that's a really cool company. If you are interested, there are always some openings in the website, so you can just go there and check what's available. And these are the contents of my talk. First, I'm going to talk about what it is, what makes it unique and different from other languages, what are the main features of that. Second, I'm going to talk about the current state and what's going to happen in the future. And in the third part, I'm going to try to convince you to learn it or use it, and finally some questions and answers. So let's jump into what is Eta. And before that, a bit of history of programming languages. You go back to the beginning of times. That's 1950s for the programming world. There were two different branches in there. One was functional and imperative. They both appeared roughly at the same time, starting with Lisp and with Color Frontend in the other side. So the functional one was dominated by academics, and it was a very focused on research, like finding new ways of doing things with programming languages, while the other one, the imperative one, was early adopted by industry, and they started like writing their businesses using those programming languages. So you can see that there was a lot of action at the beginning in this area, booming around here. That's when object-oriented appeared, and more recently, things started to get mixed. So languages started to get in features from functional programming languages and mix them all together. Nowadays, in the very recent history, there's not a lot of new things appearing in that area, but there's a lot of new stuff here. So, for the purpose of this talk, and Eta is around here, and then I've marked in yellow some languages that were ancestors and influenced Eta in some way. Like the first one, Java, who is immensely successful language that has been used in the industry for many years already. But you already know about that because I'm assuming that you are all Java or you are related with Java in some way. And the other one that maybe is not so popular, it's Haskell. How many of you have heard about Haskell before? Okay, quite a lot. It's not so bad. How many have you ever written anything or read a book or a tutorial? Okay, some people. That's not bad. So, what's the deal with Haskell? It's if you look at the range of languages from imperative to functional, the spectrum. So Haskell is just in the functional side, all to the extreme. So it's as much functional as you can get if you want to do functional programming. Also, it was for a few years very academic. People were thinking like, why, if it's so good, If it's such a nice language, why it's not used more in the industry? What's wrong with that? And some people thought like, okay, maybe if we make it compatible with Java, that would make things better. No, it would be much easier to interoperate with that. Interoperate, sorry. And the first attempt to do that was Fridge. So that it's basically same as Haskell with a few modifications. Took some traction, but not much because it wasn't exactly the same language as Haskell. The second attempt was Eta, which has barely 2 years of existence. And in this case, what they did is, okay, we're going to take Haskell as a language and the compiler, and we are just going to rewrite a backend for it. So instead of producing native code, it's going to produce Java bytecode. So that automatically gives Eta, makes all the libraries in Haskell available. All the code, you can basically compile it and run it in Java, or in the JVM. And from now on in this talk, when we talk about the Eta language, it's basically Haskell, with some additions that let you import and run code from Java, but it's the same language, basically. So what makes it special? These 5 features, the combination of them. So because there's no other language that has all these 5. Starting with the first one, functional. There are a lot of functional languages out there. We have Clojure, we have Scala, partially functional. Well, you can go full functional with it, but there's Erlang. So that's pretty common nowadays. A lot of imperative languages are getting functional features. So and it's becoming pretty popular at the moment. Pure, that's a very unique one. There are not many other languages that are pure. That means that there's a clear distinction between code that does side effects and code that doesn't. And you try pure. Well, I will explain all of them in detail later. Statically typed. That's pretty common nowadays as well. Java is statically typed, but maybe Eta it's a bit more than that. No, it's really statically typed. Other languages let you escape the static check-in in types. The opposite of statically typed is dynamic, and with languages like Clojure, Python, JavaScript. Lazy, that's again something quite unique. There are not many languages that are unique, and that's because to be lazy, you need to be pure first. Otherwise, you get really nasty things going on in there. Lazy means that you only evaluate things that you need, so you don't really control the order in which they happen, which if it's not pure, it's just going to make things difficult. But in this language, they make it okay. And the last one, I mean, these 4 first, Haskell also meets them. And the last one is it has JVM interoperability, so you can call code from Java and back. So let's go with functional. So let's define what's a function in here. Probably you remember from primary school, you get this thing here. You have 2 sets, elements from one to the other. That's what a function is. So the first set is the input. The second one is the output. So whenever you have a value in the input, it always points to a single value in the output, always the same. That's another way of seeing representing a function, input, output. The output is entirely determined by the input, and nothing else affects that. So definitions of functional programming. So everything is an expression. There are no statements, no variables, no for loops. An expression is something that you can evaluate eventually to one value. Functions can be treated as values. So that's another definition. It means that same as you do with primary basic values in a language, you can also treat functions as that. You need a function as a parameter or some other place, and you just can create it there, creating a lambda. You don't need to define the function somewhere else, and then you can just do it in place and pass it around. And the third definition It's higher order functions, which means functions that have functions as input and return functions as output. One example of that is the composition function. That's how you write that in Java. I think you can do that since Java 8. So it's a bit messy with the types. There's a lot of things, a lot of boilerplate when you define that. That's how you do that in Eta. The first line is just the types. The second one is the implementation of the function. So the first line is entirely optional. If you don't put it there, the compiler will figure out. And you can see that there is a function. It takes another two functions as input and returns a lambda, which is another function. So if you can do that, basically your language is functional in some way. Pure. So in this case, we have similar to the picture before. Pure means you have some black box in here. There's an input and output. The output only depends on what comes in here. For impure, that doesn't have to be anything like dirty, it's just a different concept. There are some things that can happen here. There's some context outside, and things can get inside and affect the output. Some things can get outside of it and affect the context of the function. So it's a lot more difficult to reason about these kind of functions because anything can be there, can happen in there. You get interaction for different places. If you can make functions in this way, it makes things a lot simpler to reason about. And so what are examples of side effects? So I/O, any reading or writing for a network, reading or writing from disk database, getting events from the mouse, from the keyboard, printing things to the screen. Exceptions, you have an exception somewhere in here. It will stop the flow of your function. It will return it. You don't even get an output from that. Threads and logs, if you have logs inside here, another code outside of that can hold that log and your function will never finish, or well, that's a possibility. Randomness, you have randomness happening here. It could affect the output, even if you pass the same input. Implicit context, you are reading from external configuration files inside the function or environment variables that can also affect this. That's the bigger one, having shared state, not only shared, but having state, which is holds outside of the function. For example, you have a method in an object. If it's reading or writing from one of the fields in the object, then it has some kind of state. So that's impure as well. Logging, that doesn't affect, you have some logging here, it doesn't affect the output, but it puts something gets out. You write into some file, it goes into the disk, and it can fill the disk and stop the whole thing. I mean, it has some effects outside. So the nice thing about Eta is that it makes these effects explicit in your functions. When you define them in the type, you need to mark or put a flag or tag like this is impure, this is pure, and then you really start treating these two different types of code separately. So these are saying the languages shape the way you think. So you are used to mix and match impure and pure code. Maybe you are not aware of that you are doing these things, but once you go to Eta, you really have to keep it in your head. Yeah, so the type system is going to force you to distinguish between these two types of code. And it helps you just keeping those apart. So this is a very simple example of a little program. Let's say you have a file. Each line is one department, and those are the ages of the people in the department. So what you want to get is the maximum and minimum from each department and see what's the difference. So you get what are the difference, the range of ages for each department. So how would you write that in Eta? So something like that. It's not a lot. It's very concise. So you don't need to really understand all the aspects because it's quite a different language, and you know Java, it doesn't really map exactly, but in a summary, what the work that you have to do is split the file in lines, then for each line, split it in words, convert it to from a string to a number, calculate the maximum, the minimum, and then subtract that. And finally, that's where you read the file, and that's where you print it. So in this code, the red is what are the parts that are impure. The greens are the ones that are pure. So if you look at these expressions from the compiler point of view, they will have very explicit types at which ones are doing impure stuff. So immutability, that means that you cannot change things once you create them. There are no assignments, there are no variables. The only thing that you have is a binding. So you have an expression and you give it a name. And that name stays there forever, at least in that scope. So if you have, at some point you define x equals 5, then you cannot say later x equals 6, because that's inconsistent from the point of view of the compiler. Your data structures don't change ever. So let's say that that's how you build a list that is immutable. So it's kind of a linked, single linked list, and you want to add an element to this list. You put it there, and you still keep the old one. So you have both of them. So you actually, it's like making a copy, but without making a copy, you still share all the internal structure of that. So common problem when you are dealing with mutable languages is like you have some object, you want to pass it to a function, and you don't really know. Do I have to make a copy? I don't know. It's going to someone is going to modify inside or outside. They are going to affect each other. That's not a problem anymore because you cannot change them. You can when you restrict the mutable state, I mean, you remove one of the biggest obstacles for concurrency and parallelism. You know, like having logs that make sure that they sync to access this mutable state. But if you don't have mutable state, that's not a problem anymore. Sometimes you need it because there are some algorithms that naturally are more efficient when they are mutable. You can have it in that case, but it's very restricted. And you should only use that. It's a clear optimization. So, and if you use mutability, you need to make it explicit as well in the type system. So a function that is mutable will be automatically be considered as impure. Statically typed, as I mentioned before, you know, Java programmers really know quite well what does it mean being statically typed. It means that the compiler is going to check the type of values that you have in your program, and when you combine them, it's going to make sure that they match. And you're not doing anything stupid that will explode later when you run it. So the difference with Eta is that you can make types a lot more precise. You can do a lot of sophisticated things in there. You have some data, business data, and you want to model that, you can create a type that is exactly that, nothing more and nothing less. You don't have to have states of data that don't match the business. You can do exactly that. So your invalid data, you cannot really represent it as part of this type. With types comes some pain, because you have to be very explicit, at least in Java, for example. You have to write all these types. And when you use generics, they become really, really big and complicated. In Eta, you can avoid it, almost all of them, because the type inference is quite powerful. It doesn't work just in one statement. It makes sure that all your program, the inference works globally in your program. So you basically, if you don't want, you don't have to type anything to add any type. The compiler will do it for you, and sometimes it will do it even better, because it's always going to find the most general type for your code. So one thing that you create a lot is functional, like pure functions, and with generics are really, really restrictive in terms of how many implementations can you make of them. So if you have this type of functions, like you can, sometimes you only have one option on how to write that function. This is an example of that. In this case, f is a function. This is just a typed declaration. A is a generic parameter, and the same generic parameter, the same type for the output, input and output here. So how many ways do you have of implementing this function? So you don't know anything about A, absolutely anything. So you cannot look inside. And you cannot create a new A because you don't know anything about it. You know how to put values in there. So the only real thing that you can do with this function is to take it from one side and pass it. This is the identity function. If you do the same in Java, you have this. That's the equivalent type. And it's a bit more verbose, but in this, how many implementations do you think you can make of this? You can do anything you want in there. The X is an object, it's a class object. You can convert it to a string. You can hash it. You can use reflection and get what is there inside, and you can use that information to create new other versions of that. You can also add log statements there. You can do anything. You can send a command that deletes the database. I mean, there's no restriction at all about what you can do in this function. At least the compiler is not going to check anything, really, because you can bypass that. In this case, you can't. So if you want, for example, you want to log the value of A, this type doesn't work for you. You need to do something else. You need to say, okay, I want to log A, so I need to make sure that you can convert it to a string, and that's the constraint that you give in there for that. And when it writes, it needs to be an I/O, because otherwise, I mean, it's going to affect the external environment. It's going to write somewhere, so you really need to do that. But I/O, you can do anything as well with I/O. You can delete databases as well. So if you want to be more precise, you can do that. You can say this is exactly the same function, but in this case, you can only write strings to a log. And the compiler will not let you do anything else. That the type already tells you what the function can do, and it's checked. So you cannot bypass that. So you get code that is a lot safer, and you don't have to write so many tests as with dynamically typed languages. If you have ever written anything in Python or JavaScript, you know that sometimes you have to write more tests than code itself, like business code. In this case, you can just limit your test to test business rules or business logic. You don't have to write tests to check that things match and they're not going to break at runtime. So that also helps a lot when you are maintaining code or refactoring. You make a change somewhere, and then all the places that don't match that type will just pop up as compiler errors, and you can just go one by one until you fix all of them. So this is a small joke here. So you have dynamic typing in one side, static in the other. We're trying to build this puzzle in here. In dynamic typing, all your pieces are exactly the same shape. You put all them together, it looks like you are building something, you finish really quick, but you may get it wrong later when you are trying to look at the picture. In the other side, your pieces have shapes. Those are, imagine those are the types. So it's some additional thing that is going to make it more difficult at the beginning to get it right, but you have more confidence that when you finish, everything will be good. And this guy in the right is going to take a lot more time to do it, but the thing here is you want to do is not putting all the pieces together. You want your program to be correct. So I think eventually the guy in the right is going to have that objective faster. And this example is a bit stupid. It's obvious that this is wrong, but if your puzzle is like 10,000 pieces, then it's not so obvious that you have some piece turned in the wrong way. Laziness, it means that you only evaluate expressions that for which you need a result. So the client of your function is going to say, okay, give me the next thing from there, and the function is going to do enough work to answer that question. The opposite of lazy evaluation is strict, and most of the other languages out there are strict. In Eta, lazy is the default. You can make things strict if you want, but the default is Eta. So if one thing that you can do with laziness is define infinite data structures. Data structures. As long as you don't request all the values in there, it's fine. It's like a generator. And in other languages like Java, you have streams that are lazy sequences, but it's very restricted. In Eta, you will have not only streams or lists. You create a tree, it will be lazy. You create a graph, it will be lazy as well. So it's an example of one of these infinite data structures. Ones is an infinite list of ones, number ones, one after the other. It's defined based on itself. So what is ones? You append one at the beginning of ones. So how can this thing work? I mean, it doesn't make sense. It's because it's not going to be evaluated when you write it, only when you start getting elements out of it. So you get, give me the first element of ones, okay, here it is. Give me the second one, okay, then I have to check ones, but what is ones, okay, it's ones. And then that's the next element. There's another example like that, the Fibonacci sequence. It's the whole Fibonacci sequence, all the elements in there. You can see that it's defined based on itself. It's very concise too. And the real power of being able to define these infinite data structures and combine them lazily is that it's easier to write software that composes. So one side you have the generation, then you have transformations, then you have when you have to end consuming that. And you write them separately, you put them together, and they still behave efficiently. They only do the work that is needed. That's another example. You pass a list to this function, and you want to get the nth element once you have sorted it. So this function is a composition of two things. You first sort it, and then you index and get the n element. So you want to get the third element of this using this function. So you are sorting it. I mean, in the definition of the function, you are sorting it first, but it's not really happening. If sort is lazy enough, you will. I mean, once you request the third element, it will only sort enough of that list to return you the third, and the rest of the list it will remain there, just waiting until you want more information. So it's still going to behave efficiently in this case. Problem with that is sometimes very difficult to predict when the evaluation will happen, because imagine you want to debug that. So the execution of the evaluation is not going to happen in the same order you have written in your code. Only when you need is some lines here, some lines there. So that's why if you have side effects mixed with that, it's going to be really, really a pain to debug. But that problem goes away because it's a pure language. Abstractions. So I want to talk in this slide about object-oriented design patterns. They were a big improvement. At some point, it allows us to build bigger programs, more complicated. And there was some famous book where you have all these patterns in there. But in my opinion, the problem is that it's written in a book. Why it's not written in a library? I mean, it's so widely used. These problems appear so often. Why are not libraries that people don't have to write again? Or at least the interfaces that people can reuse, and you have those in the base libraries of your language. I think the problem is that you can't. The language is not flexible enough, or it doesn't give you enough abstraction to do that. So you end like in a local maximum here. You can move higher in abstraction. So you have to do some drastic change. Either you modify the language or you just jump to a different one. And Eta it also has a ceiling in there, but I think it's much higher. So in Eta you have functional design patterns too. They are different from the object-oriented. Usually they are coded as type classes, which are something similar to interfaces. These are the names of some of these patterns. You may be familiar with them, maybe not. I think they are going to become more popular. I think at some point people will start using these things in other languages too. Java interoperation, I think that's what you would expect of any language that has Java interoperation. You also have other languages that do that. Clojure, Scala, it's probably the most important one because it allows as well object orientation, so it's very natural to do it. In Eta, it's a bit more unnatural because the two paradigms are different. So it's not so easy to, well, it's not easy to do object orientation in a pure functional programming language. Exporting and importing static pure methods is the easiest thing you can do. But obviously you need access to the whole thing. You need to have access to objects, classes. So you box them into a wrapper. That goes fine. You cannot simulate object orientation in some way. You can import code from Java into Eta, and you can export Eta code into Java, as you would expect. All the primitive types are marshaled from one language to the other when you pass it as in parameters. And you can even simulate inheritance via some type advanced extension of the language. So this is a small example because I wanted to show a bit more code. I guess you know what's the glob patterns, the ones that you use in the command line when you are looking for files. You can have a star, which means any character, or a question mark, which is one character. Usually you will implement that with regular expressions. You transform the pattern into a regular expression and use one of the existing libraries. But for the benefit of this exercise, let's try to implement it. And I looked for some code from Java or outside there, like in some standard library. I found one implementation of this in Java Commons IO, Apache Commons IO. So that's the code that does that. It's small. I don't intend you to read it. I just want to show you how complex it is. It's using all mutable arrays, for loops, a lot of conditionals. I can guess that it was very difficult to get this code right, and you have to write a lot of tests to do that. And then I tried to do that in Eta, and that's the result. I mean, so less code. And you may say, okay, maybe you choose the example that really fits, and that's right. I mean, this functional style really fits this problem because about parsing, and that's something that functional programming languages do really, really well. But how much simpler would be to write this code if you have the chance? If you know about functional style, why wouldn't you do it this way? I mean, once you know this, you can even write in this way in Java. And that's the implementation in Java. It's not as efficient as the Eta one because when you do substrings, you actually make the whole copy of the string instead of taking the shared part. But it's so much simpler than the previous one that I showed before. So if you have these two different ways of thinking about software, how to design or solve problems, then you can choose one, the one that adjusts or makes the code easier. You don't have to do it in the imperative way all the time just because it's the only thing that you know. So what's the state of and the future of this language? So there's a main company behind that. It's called Typelit. These are the two founders. They're both computer engineers. Raul made the first version of that, took in the compiler from Java and writing the backend. And Jyotsna did a lot of other things like around tooling, documentation, and building the community. So it's quite impressive with what these people did in only 2 years. They have a full language working, they have an environment, they have tooling, they have people involved in their project. There are a lot of open source contributors to that, mostly Haskell developers that want to use that in their day-to-day work. And the main focus of this, of their goal is to provide commercial support, is to provide this thing that Haskell has been trying to do for a while, like being very popular in industry. That's the main goal, like making it available for companies, provide support, provide tooling, and just translate this nice language into something that everybody wants to use. It's still an earlier stage. They haven't reached version 1 yet. But I think you can start writing production code already. It's quite robust. The thing is, because it uses so much of the Haskell environment, they got that for free. So they have all the Haskell libraries available. Almost, I mean, for some of them, you still have to make small changes when they are not complete, when they have some native code in there. But you have all Java code and all Haskell libraries there. You don't have to start writing your own, like with a completely new language. It's just there for you to pick up. You have a package manager with handles dependencies and versions and a nice build tool. You have different installation methods that you can use to get it running for the first time. You have Gradle integration. You want to put it inside some Java project that you already have. That's the main website. If you want to learn more, that's the first point to go to. That's where the code is. It's open source. You can also play with that and take a look. And if you really want to start with this language, you can just jump into this tour. It's an interactive website. You can just go there for instructions without having to solve anything. And you have all the material and tutorials from Haskell, because it's the same language, basically. So that's all available. And that's where the community is. You have some links to Twitter accounts, chat rooms, or some conference where the two founders have already presented the language. What's the future? Very important one, having a plugin for IntelliJ. That's at work at the moment. It's coming. That's what every developer wants to make their life easier. Binding for big data projects. They figured out that Scala got very famous because it's used to write things like Apache Spark, and they want to do the same. Basically, they want to eat a bit their cake. Soon you will have direct Java interoperability. Right now, you have to write a lot of statements when you import things from Java, but probably that can be automated. So that's coming soon. There's a converter from Java to Eta. I don't know if you want to use that because it's not going to write functional style code, but it's there. Very strong focus on documentation and tutorials. That's something that people complain about Haskell most of the time, but it's one of the main focuses of Eta, because they don't want to repeat the same mistakes. And there's a lot of documentation in the website already, but mostly focused on the part that is missing, interoperation with Java, which is the part that is unique from Eta. Some plans to make it not only for Java, but also for produce native code or running Android. And I think one of the big factors of the success of Scala and Clojure is that they were able to run in the JVM, and you could integrate them in your project gradually. You don't have to remove or scratch all your code and start writing a new thing. You can just, okay, let's write the unit test in this new language or this small module, and then you link it with the rest. I think Scala and Clojure got that right, and Eta wants to follow the same path. So you don't have to do all or nothing. You can do a little of it. It's easier to integrate that with existing code. So why would you use it? So first, imagine that, this is a new language. You shouldn't really go in there and try to put it in production the first day without knowing a lot about it. But by learning it, you can actually improve how you write code currently in different languages. So one thing that you will learn is to think functionally and a bit more based on mathematical foundations. So you will learn a new way of designing, of thinking how to decompose problems. So it's not so much about encapsulating a state and making sure that only some other entities can access it when they need. It's about not doing state, if you can, and treat your code as data transformations. So you have input, outputs, you do some transformations in the middle, and you compose those transformations into things that are more complex. You become very aware of side effects. Maybe before you mix them all together, but once you start thinking about that, you will try to keep them separately and only combine them when you really need. You also learn to identify mutable state and use only when you need it, only when there's a clear performance advantage. There's a new way of concurrency that is not based on logs. It's based on software transactional memory. So it means that you can have some kind of transactions that you can compose together. It's a kind of optimistic concurrency, and you can compose it together, and you will not get deadlocks. So a lot of languages are picking this as well, but only Eta gives you guarantees because the compiler checks that your code is pure when you are doing these things. You get exposure to very interesting language features because Haskell was, well, still is one of the main sources of research in languages. Sometimes it gets features, or it has features now that we'll only get into other languages, mainstream languages, in a few years. So things like functional type classes, those things were in Haskell since the 80s, so 1985 or 1990, and they are only getting now into new languages. So if you know that, you learn those things, and next Java 20, when you get the list of features, instead of saying, oh, what is this new thing? I don't understand anything. I have to go and read books. Your reaction can be, oh, finally, I got that. I was waiting that for years. Now I'm going to start applying it to my code and make it better. And all these features and functional concepts are very transferable. So you can use them in other languages. And I think there's a lot of conversations of how to do that. Like you go to forums, everybody's talking about functional, how to do this in functional way. So sometimes it's a bit of hype, but I think it's well founded. Now, if you really want to start and go there at home and start using it for your personal projects or try to introduce it at work. So what can you get if you do that? So really strong focus on correctness. So the compiler is going to really make things safe for you. It's not going to allow you to do a lot of crazy stuff, and you'll get a lot of the things that were runtime errors before, you will catch them at compile time. And that really improves your feedback when you're writing. So you get errors immediately. If you have the compiler running in the background, you get it in red. You get all the errors in there just when you are typing it, not when you are running the test, not when you are running it in production. So you get it at compile time. You have to write less code, usually, like by some factor compared to Java, for example, because it's very concise. You have to write fewer tests because the type system is going to guarantee a lot of things for you. And you still keep the same functionality. Your code bases, I think, can grow bigger because they're easier to update and maintain. And refactoring is also going to be easier. Once you start working with immutable data, your data flows are simpler because you remove the whole temporal modification dimension from there. There's usually one source of your data for a given expression, and there's no other piece of code that can get into the middle and change it, or you have to think about the order in which things happen. So that simplifies things a lot. You can still use mutable if you need, but avoid it if you can. And you get this nice composable lockless concurrency. So Eta It's based on Haskell, as I said before. It's very consistent language and small one. So there are not a lot of gotchas, like things like, oh, what is this surprise? This is an exception in the language. Why is that? There are almost no things like that. At the same time of being small and simpler, you can do a lot of abstraction in there. I like this sentence that I stole from someone else that said, no, Eta has no tolerance from imprecision of thought. What that means is, when you're writing your program, you really need to think about all of it, corner cases. You cannot write code like quick and dirty to get something running without thinking about all the different paths that code can take. No, because the compiler is going to tell you, you're not thinking about this. You need to be clear about that. You cannot forget corner cases. So if you are trying to write this kind of code, maybe the compiler is going to stop you. And if you don't know how to do that, I'm sorry, you really need to think about that. So if you want to write quick and dirty code, maybe Eta is not the best option. If you want to write code that is good and complete, that's a good choice. And finally, don't depend on when you make mistakes. People tell you have to read books, best practices. You need to be really diligent, or why not let the compiler do that for you? We are software developers. We want to tell machines what to do. Let's do that. Let the compiler help us write code. So thank you for your attention. That's all.